So, objective of this discussion, the very first objective of this discussion is to explain fin performance in terms of fin efficiency and fin effectiveness. So basically we are going to define two very important terms related with the fin design, fin efficiency and fin effectiveness. And the significance of these two terms, fin efficiency and fin effectiveness, with regard to the fin design and selection. Now let us start our discussion with fin efficiency. Now, as you can see here, there is a base surface at some temperature, let's say 80 degrees Celsius, and it is attached with a fin of some finite length L. Now let us consider a limiting case. The thermal resistance of this fin material is 0, or the thermal conductivity of this fin material is infinite. Under such condition, what happens? The entire fin will have the temperature equal to the base surface temperature, for example 80 degrees Celsius everywhere. Under such condition, what is happening? If this fin is exposed to the surrounding fluid T infinity, the temperature difference will be Tb minus T infinity, because fin surface is equal to base surface temperature in the absence of any thermal resistance or thermal contact resistance or infinite thermal conductivity. So if this is the condition, this is actually the ideal condition or limiting condition. If this situation we can obtain, this will be the ideal condition, and under such condition, heat transfer from the fin surface will be maximum, and we can calculate this heat transfer using the expression Q fin max is equal to H area of fin into Tb minus T infinity. Okay. But in reality, what happens? The fin will have finite thermal resistance or finite thermal conductivity value, because of which some resistance will be offered to the heat transfer from the base surface to the root of the fin towards the tip of the fin. And because of this resistance, thermal resistance and finite thermal conductivity, temperature of the fin, as you can see here in case B, will gradually diminishing along the length of the fin. If base surface is at 80 degrees Celsius, the temperature at this distance x1 will be 70 degrees Celsius, will go on diminishing, and for example at the tip it will be 56 degrees Celsius. So here what is happening actually, because of this finite thermal resistance and finite thermal conductivity, temperature difference is not same. If I consider area A1, area A2, area A3 and area A4, temperature difference between the fin surface and the surrounding fluid will be different for area A1, for A2, for A3, for A4, A5 likewise. And depending upon those temperature differences, the heat transfer rate will be different. and that will be the actual heat transfer rate from the fin attached to any base surface. So what is point of contention? In real life situation or in reality, the temperature of the fin decreases or diminishes along the length of the fin because of finite thermal resistance or finite thermal conductivity of the material of the fin. And this reduces actually heat transfer rate from the fin of finite length. So to account for the effect of this decrease in temperature on heat transfer, we define one term, and this term is called as fin efficiency. And this is given as efficiency of the fin as Q fin, that is rate of heat transfer from the fin under actual condition, that is fin of finite thermal resistance value and finite thermal conductive value, to the rate of heat transfer from fin under ideal condition. So efficiency of the fin is given as actual heat transfer rate to the maximum heat transfer rate. So numerator is actual heat transfer rate from the fin to the ideal heat transfer rate from the fin if the entire fin were at base temperature. So this is called as fin efficiency. It is also given as eta efficiency of the fin. See what is happening? Temperature of the fin is changing along the length of the fin, isn't it? Depending upon the area, and it is varying from root of the fin to the tip of the fin. So this will be the actual heat transfer rate to the maximum possible heat transfer rate when the entire fin is at base temperature. So eta fin can also be given as the H is going to remain same for the fluid, 0 to A Tx minus T infinity over A into Tb or Ts. Let's say I am taking Ts. So this way I can find out the efficiency of fin. For example, in our case, let's say temperature at this point of the fin is Tx1, temperature of the area is Tx2, and temperature of the area A3 is Tx3. That is, at this point temperature is Tx1, Tx2, Tx3, and the fin is exposed to the fluid T infinity. So how can I calculate efficiency of this fin under consideration? 0 to A1 Tx1 minus T infinity plus A1 to A2 Tx2 minus T infinity plus A2 to A3 Tx3 minus T infinity over total area of the fin, that is maximum heat transfer if the entire fin surface is at base surface temperature. So this way I can calculate fin efficiency. Basically, in very nutshell, I can say because of temperature decreasing along the length of the fin, heat transfer rate decreases from the fin surface. And in order to account that heat decrease in the heat transfer, we introduce a new term called as fin efficiency. For example, for infinitely long fin, Q fin is nothing but root of HPKC Tb minus T infinity, and maximum heat transfer rate from the fin under ideal condition is HA fin Tb minus T infinity. So this will be 1 over ml. For insulated tip fin, rate of heat transfer from the insulated tip fin, root of HP KAC TB minus T infinity 10 of hyperbolic ml to the HF in TB minus T infinity. So it can be given as 10 of hyperbolic ml over ml. And in data book, we have seen this. Similarly, okay, so this way I can calculate efficiency of fin under different cases. Okay.
Fin efficiency significance. In order to understand the significance of fin efficiency, let us consider expression for fin efficiency of infinitely long fin. So efficiency of long fin can be given as Q fin over Q fin max. And efficiency, that is rate of heat transfer from fin of infinite length, can be given as root of HPKAC TB minus T infinity over maximum rate of heat transfer, that is H area of fin into TB minus T infinity. After taking into consideration this formula, it will become 1 upon L square root of HP over KAC, and this entire term is M. So it becomes 1 over ml. Now, whatever discussions we are going to do, the outcome of those discussions will be applicable for fin efficiency of all type of fins. Now, based upon this expression for efficiency of infinitely long fin, let us have some general observations. Observation number 1, efficiency of fin is equal to 1 over ml is equal to 1 over large number. From this expression, it is clear fin efficiency will be decreasing if length of the fin is increasing, or vice versa. Second observation, by a small value of ml, the fin efficiency increases when the length of the fin is reduced to 0. That is, there should be no fin at all. Now what happens? In order to enhance the heat transfer rate from the base surface, we provide some fin of finite length, that is L. But from the expression of the fin efficiency, it can be concluded that fin efficiency will be maximum when length of the fin is reduced to 0. That is, no fin at all. So these are two contradictory statements. So because of this, when we want to select, or when we want to maximize the performance of the fin, we cannot take length of the fin as the performance maximization criteria. So based upon these two observations, what is the significance of the fin efficiency? Fin efficiency is considered as a criterion or parameter to select fins of different shapes, like rectangular, square, circular, or triangular, and of different materials. Let's say we want to enhance the heat transfer rate from the base surface at some rate Q, and we have designed different fins of different materials and of different geometries, like rectangular, square, circular, or triangular. So out of these fins of different geometries and made up of different materials, which fin to select in order to enhance heat transfer rate? So for selection of fin based upon these two criteria, fin efficiency will be the design parameter or criteria. So that is the significance of fin efficiency. Now, next fin performance parameter is fin effectiveness. Now, fins are used to enhance the heat transfer rate, but in order to enhance the heat transfer rate from the base surface, the fins are recommended only when the enhancement rate justifies the cost and complexity of adding the fin to the base surface to enhance the heat transfer rate. Similarly, there is no assurance that just by adding the fins, we are going to enhance the heat transfer rate. It is against the general belief that fins will always enhance the heat transfer rate. It is not like that. The performance of the fin is judged on the basis of enhancement of the heat transfer relative to the no fin case. So if I want to judge the performance of the fin to enhance the heat transfer rate, I will calculate the heat transfer rate from the base surface with fin, and then I will calculate the heat transfer rate from the base surface without fin. And if the rate of heat transfer enhancement by adding the fin is substantial, only in that case, I am going to select the fin. I am going to select the option of attaching fin to the base surface. So the performance of fins expressed in terms of fin effectiveness is defined as, so here we are going to define a new performance term, fin effectiveness, and it is given as heat transfer rate with fin to the heat transfer rate without fin. And in mathematical form, it can be given as heat transfer rate. It is the ratio of heat transfer rate with fin to the ratio of heat transfer rate without fin. That is HAB TB minus T infinity. Now, in order to understand the significance of this expression, let us consider a base surface of area AB and temperature TB, and it is exposed to the fluid T infinity. Okay, so had there been no fin attached to this base surface, heat transfer rate will be, that is Q without fin will be H into area of the base surface into TB minus T infinity. In second case, let's say the same base surface is there, but now I am attaching one fin to this base surface. So in this case, rate of heat transfer with fin will be what? Rate of heat transfer from this base surface plus rate of heat transfer from this fin. So effectiveness of fin can be given as rate of heat transfer with fin to the rate of heat transfer without fin, where AB is the cross-sectional area of the base surface and Q no fin is rate of heat transfer from this base surface area when there are no fins attached. Now, based upon this fin effectiveness criteria, it is justified or it is recommended to use the attachment of the fins to the base surface to enhance the heat transfer rate only and only if the value of this effectiveness comes out more than 5. If this effectiveness value is more than 5, the addition of the fin will be more justifiable in terms of maximum heat transfer enhancement and less cost and complexity. So now we have two criteria basically to define the fin performance. One is fin efficiency, another is fin effectiveness. Fin efficiency will be used to select amongst the fins of different geometries and of different materials. And fin effectiveness will be used to decide whether we have to attach the fin to the base surface or not. Even after attaching the fin, if the heat transfer enhancement is not substantial or not economical, we are not going to attach fin to the base surface. That will be decided by the fin effectiveness parameter. Once again, in order to understand more about the fin effectiveness, let us once again calculate the fin effectiveness for an infinitely long fin. So we know for infinitely long fin, the rate of heat transfer from the fin will be Tb minus T infinity into square root of HPKAC, and heat transfer rate from the base surface without fin will be HAB minus T infinity. After simplifying this, I will get this expression, square root of K into P over H into AC, where K is the thermal conductivity of the fin material, P is parameter, H is convective heat transfer coefficient of the surrounding fluid, and AC is the cross-sectional area of the fin. Now, based upon this expression for fin effectiveness for infinitely long fins, let us have some observations. These observations will be applicable to fins of all types, whether it is insulated tip or infinitely long fin or fin of finite length, losing heat at the tip. So observation number one or conclusion number one, as you can see here, effectiveness of the fin is directly proportional to square root of K, that is thermal conductivity of the fin material. So what I can conclude, more will be the thermal conductivity of the material of the fin, more will be the effectiveness. And we know copper, aluminum and steels, these materials have highest thermal conductivity amongst the other materials, among the other materials. So fins are generally made up of copper, aluminum or steel. But since copper is a costly material and heavier, so as the steel, so generally fins are made up of aluminum because of its cost, good value of thermal conductivity and weight, and also its ability not to get rusted in the moisture environment. So the first criteria is to select is thermal conductivity. More will be the thermal conductivity, more will be the effectiveness. Second conclusion I can draw, effectiveness of the fin is also directly proportional to square root of P over AC. That is, more will be the ratio of P over AC, more will be the effectiveness of fin. Now, what is its physical meaning? In order to have this ratio P by AC more, value of perimeter will be more and area of cross section will be as minimum as possible. And its physical meaning is, instead of fin of larger diameter, we must use of fins of thin cross section or slender cross section. So for that, we generally select thin plate fins or slender pin fins. So instead of a fin of larger diameter, we can use fins of small cross-sectional areas like that. This arrangement will give more heat transfer rate as compared to this arrangement. Another important conclusion I can draw from here effectiveness of fin is also directly proportional to inverse square root of 1 over h. So what does it mean? H is the convective heat transfer coefficient of surrounding fluid. So more will be the convective heat transfer coefficient of the surrounding fluid, less will be the effectiveness of the fin. So if fins are exposed to the fluid which is having higher value of convective heat transfer coefficient, in that case fin will not be able to enhance the heat transfer rate. Fins are attached to enhance heat transfer rate only when they are exposed to the fluid of low value of convective heat transfer coefficient. And among between liquid and gases have low value of convective heat transfer coefficient. So fins are useful in enhancing the heat transfer rate only when they are exposed to the gas rather than liquid. So let us have look one more, another elaboration of all these three important conclusions. So conclusion 1, let's say there are 3 fins attached to the base surface. Let's say this is made up of copper, it is made up of aluminum, and it is made up of steel. So copper, being a highest thermal conductivity material, will give more enhancement in heat transfer rate. This is the conclusion 1. Number 2, let's say I want to enhance the heat transfer rate from the base surface, and I have designed fin of certain perimeter and cross-sectional area. And let's say I am attaching that fin of given design perimeter and cross-sectional area. Instead of this single fin, if I attach the thin fins of same perimeter but a smaller cross-sectional area, so this arrangement will give me more enhancement in heat transfer. That is conclusion number 2. So instead of a single fin of larger diameter, we can cut that small fin of larger diameter into smaller fins of smaller diameter, and if we attached those slender or thin fins to the surface, they will make the heat transfer rate enhancement more. And conclusion number 3, let's say I have attached these fins to this base surface. In this case, they are exposed to the liquid. In the second case, same base surface is there, same fins made up of same materials are there, but in second case they are exposed to the gases. Now what happens? Convective heat transfer coefficient of gases is much smaller than convective heat transfer coefficient of liquid. So in second case, fins will be more effective in heat transfer enhancement rather than in case 1 because of this factor, because of this relationship of effectiveness with respect to convective heat transfer coefficient. So this way I can understand the significance of fin effectiveness. And I can use fin efficiency as well as fin effectiveness, these two performance parameters, to design and select appropriate fin to enhance heat transfer rate from base surface. So after watching this video, students will be able to explain fin performance in terms of fin efficiency and fin effectiveness, and you will also be evaluate the significance of fin efficiency and fin effectiveness with regard to the fin design and selection to enhance the heat transfer rate from base surface. So thank you for your passionate listening. Happy learning.